Yeah. All right. So I would like to thank you again for the introduction and also the invitation at this event, and congratulate you to organizing such a great event for young researchers. So I would like to thank in particular the Indian National Young Academy of Sciences, INYAS, the Assam Academy of Mathematics, and the Department of Mathematics at Jawaharlal Nehru College in Assam, and of course the entire organizing committee. All right, so I would like to introduce timescales today and then go a little bit into the applications in the second part of the talk. Timescales was introduced in 1988 with the PhD thesis of Stefan Hilger that you see here on the left, who is now a professor at the University of Eichstätt-Ingolstadt in Germany. And the theory of timescales is really trying to provide a framework to unify the discrete and the continuous time domain and calculus, and therefore addresses one of the aims that was mentioned by Eric Temple Bell, who writes that a major task of mathematics today is to harmonize the continuous and the discrete, to include them in one comprehensive mathematics and to eliminate obscurity from both. And this is exactly what timescales is trying to do by unifying that calculus theory. Now, since 1988, a lot has been developed. There are different areas or sub-areas in timescales that are being studied. One of them is linear and nonlinear, so-called dynamic equations. That is essentially the analog of differential equations on timescales. And of course, you can then also look into delay dynamic equations and applications that you see here. You can also study partial dynamic equations and stochastic dynamic equations, although this field is not as developed as the others. That's why I provided some references here in case some of you are interested. Now, recently, there's also an interest in fractional calculus, right? I know you're going to have a talk about that as well. And so you could also consider fractional timescales and study that. There's a book recently in 2018 from Svetlin Georgiev. Now, if you go to MathSciNet, that's one of the biggest databases for mathematics publications, and you type in a title search for timescales, you actually obtain a little bit short of 3,000 publications that are listed containing in the title timescales. And it also provides you with the authors and their respective number of listed publications. And you see here, for example, Lee Yong-kun, who is, for example, working on delay dynamic equations and applications to neural networks. Now, two names that I would like to point out here as well are the names Martin Bohner and Martin Bohner that you see here, and Alan Peterson. And unfortunately, there is, okay, sorry about that. Just had to adjust the bar. So Martin Bohner and Alan Peterson that you see here, these are two researchers that are also the authors of the two main introductory books on timescales. You see on the left, dynamic equations on timescales with an introduction from 2001, and then the follow-up book, Advances in Dynamic Equations on Timescales from 2003. And since the first part of this talk is going to be an introduction to timescales, I heavily rely on that Dynamic Equations on Timescales book from 2001 and will use the definitions and notations of this book. All right, now a timescale is an arbitrary non-empty closed subset of the real numbers. So that sounds pretty broad, right? You do have the restriction of being closed though. And so the first couple of examples that should come to mind are the real numbers itself and the integers. And that should be, right, if timescales is trying to unify those two schemes. So those are immediate examples. And then of course you can consider age set. So age set is a timescale where you essentially have points that are not one apart from each other, but with a distance of h. All right. And so the next example that is common and finds applications in physics is the so-called quantum calculus. So in this case, it's kind of like a multiplicative timescale, if you will, because you start out, for example, with q to the 0, and for q not being 0, you get 1. And now you're gonna jump to q to the 1, q squared, q cubed, and so on. And especially if q is greater than 1, which is commonly assumed when you consider dynamic equations on quantum timescales, then you don't have to worry about it not being closed. If you were to pick q less than 1, then you would want to certainly include the 0 as well. All right. Now, of course, you can have any combinations of those traditional examples. You could have a union of an interval and an isolated points, which is very important and helpful when you model, for example, populations that are cycling between seasons where they behave more continuously and then rather go possibly into hibernation and behave rather discretely in another season. And of course, you can think of many other examples. Here's just one where you define it through a sequence, including the limit point. Now, there are operators on timescale, specifically the forward jump operator and backward jump operator, that help you describe a timescale. And the forward jump operator, denoted by sigma t, is essentially the closest right neighbor. So that is the infimum of all the points in your timescale that are greater than t. And similarly, you can define this also for the left side, and then it's called the backward jump operator. So that would yeah, sorry. Hello?
You please continue. There is a disturbance.
Oh, okay, sorry. Okay, so the backward jump operator identifies the left closest neighbor and is usually denoted by rho of t. So we see here an example where we have a closed interval from 2 to 3.2 and then some isolated points. And of course, we want to include those endpoints 2 and 3.2. So if we are interested in a forward jump operator at 3.2, that is denoted by a sigma, and that would be the right, the closest neighbor to the right, which in this case would be your 3.8. You cannot get any closer than that. So the sigma of 3.2 is 3.8. However, if you're coming from the left, you can get arbitrarily close, as we do have a closed interval here. And since you can get arbitrarily close, the supremum of all those points on the left is just the value 3.2. Now, those forward jump operators and backward jump operators also help you classify points in timescales. So depending on whether you can get arbitrarily close on both sides, you would be called dense. So this would be a point where you can get arbitrarily close from both sides, while a point would be called isolated if you cannot get arbitrarily close from either side. And of course, then there are these mixed cases where, in this case with 3.2, as we saw, you can get arbitrarily close from the left, but not so from the right. So that would be called right scattered, because you have to jump to the right, or you can equivalently call that left dense. Okay, and then similarly, you can, in this case, there is no such example, but you could, of course, equivalently then define left scattered or equivalently right dense. Now, we see here a table again for those very typical examples. If you were to pick the real numbers, then you can get arbitrarily close to any point. So that means that your forward jump operator is just t, and also the backward jump operator is t. Now, there is one additional operator that we will see throughout this lecture coming up, and that is the so-called graininess function. And that is nothing else than the distance to the right next neighbor. So that would be sigma t minus t. And so in the real case, where you can get arbitrarily close from the right, that graininess would be 0. That's something that I would like you to remember, because it will play a role as we go through some examples. Yeah. All right, another typical example, of course, are the integers. In that case, your points are always in a distance of 1. So the next neighbor would be t plus 1, while the previous one must have been t minus 1. And so the graininess, that's the distance to the right next neighbor, is independent of t, it's always 1. And of course, for h set, it would be h. And in the quantum calculus, for, again, here, I'm assuming q to be greater than 1. In that case, the next time point that we would consider is q times t, right? It's this multiplicative time domain that I did mention before, while the previous point must have been t q to the negative 1, right? Because you had to multiply a q to get to t. And so if you were to take the distance, you would take sigma t, which is qt minus t. So you end up with a graininess of q minus 1 times t. All right. Now there are some properties that we would want functions to have, and we will see a very specific set of functions throughout this lecture. And this set of function has 2 properties, one of them being RD continuous. The RD stands for right dense. So as the name suggests, we would call a function that goes from a time scale to the real numbers to be RD continuous, denoted with a CRD, if the function is continuous for all right dense points and its left-sided limit exists for all left dense points. So it's a little less restrictive as the traditional continuity. So certainly all continuous functions are RD continuous, right? Because not only would their left-sided limit exist, but it would also be equal to the function value, which is something that we don't require for RD continuity. And so you see here an example where you have the non-negative integers union with this sequence where n is going to 1. And so you would have again 0 and then 1, and in between you have that sequence converging to 1, but it's converging to 1 from the left. So the point 1, right? The point 1 is the only one that would not be isolated. It would be left dense, but since for left dense points, all we require is the left-sided limit exists, well then certainly this limit exists, because the limit of ft would then just go to 1, but it does not have to be equal to the function value at 1, which would be 0. So this is an example of a function that is considered to be RD continuous, but not continuous. Now, the second property that we would want functions to have is, and again, of course, it depends on what you're studying, but a common and nice property is for a timescale function to be regressive. Now, that means that 1 plus the graininess times the function value would never be 0 for any t. And we would say it's positively regressive if 1 plus mu p is greater than 0 for all t. And so the set of regressive and RD continuous functions, the 2 properties that I mentioned now, is denoted with this script R. And if it would be also positively regressive, we would give it a super index of a plus. And this R you will see throughout this lecture very often. Now, I would like to also point out that in the real numbers, again, we want to always take a look at what happens in the real case. And in the real case, I would like to remind you that the graininess is 0, because you can get arbitrarily close to your right, from the right, sorry. And so 1 plus mu t pt, if the graininess is 0, well, then you obtain 1. That's certainly greater than 0. And so every function in the reals is considered to be positively regressive. And here's another example where you see that a function, even though it's a very nice function, right? If you remember from calculus, in calculus, usually the constant functions are considered to be very nice in the sense that they are smooth. And in this case, however, that function would not be considered as nice simply because it's not regressive. And again, nice is of course very subjective and very vague here, but it would not be regressive. So and this is simply because it also depends on the time scale. So properties of functions that we know from calculus are not only dependent on the actual structure of the function, but also the underlying time domain. So that's just something to be aware of. And again, you can do a very simple example where you have the sequence that converges to 1. And if you were to choose a time point as 4/3, so simply choosing n to be 3, if you were to calculate the graininess, then the previous point was 3/2. That is for n equals 2, and this is n equals 3. And so you would obtain a graininess of 1/6. But now the problem is once you multiply this to the function of -6, you would get 0. And so this function would not be regressive because there exists a t such that 1 plus mu p is 0. Now you may already guess, right? If p would always be if that would be always non-negative, then we are good to go. All right. Now that we have these desirable properties of functions, and again, right now it's a little bit vague why that would be desired, but you can think a little bit about it as being a continuous function in the continuous case, if you want, in the reals. Now, given these two desirable functions, our set script R, a natural question is whether or not this property or these two properties are being preserved under operations such as addition. Right? We know from calculus, if you add two continuous functions, you obtain a continuous function. Now, in this case, the answer is no, and you can find a simple example here. If you choose the time domain to be the integers, and you pick f and g again to be both constant functions with different values, then if you were to calculate 1 plus mu, f plus g, you end up with 0. So the answer is no. However, if we were to define a circle plus addition, so a new operation, circle plus, which is the addition of the two functions, but then it contains this additional term mu p times q. In this case, you can actually show that the property of being an element of script R is being preserved. So again, remember, the RD continuity is not the problem. The problem is the regressiveness. And so what you want to show in order for that circle plus addition of P and Q to be a set of script R, you want to show that 1 plus mu times that circle plus addition is not 0. And if you were to now plug in that circle plus addition, right, that we see here, and factor in the mu, you can do some simple arrangements and you end up with the product of 1 plus mu p and 1 plus mu q. And so if p and q are both in the set script R, they are not 0, and so their product is not 0. So that's rather nice if you do have those two functions that contain these properties of being regressive and RD continuous, then so does their circle plus addition. And an inverse of this operation is the so-called circle minus subtraction, where you see you have the usual subtraction in the numerator, but then this additional term in the denominator, dependent on the graininess. And also in this case, you can show that the property of being an element of script R is being preserved under that circle minus subtraction. Now, if timescales again is trying to unify the continuous and discrete calculus, you know, it's a natural thing to try to choose the special case of the timescale to be the real numbers and just see whether or not we get something familiar. And so if you were to choose the timescale to be the real numbers, again, remember that implies that the graininess is 0 at any t. And so these additional terms that showed up in our, or in these operations of circle plus and circle minus, they vanish, and the circle plus addition is equivalent to the traditional addition. And similarly for the circle minus subtraction, the additional term was here in the denominator, dependent on the graininess, but since that is 0, one obtains the traditional subtraction. Now, in a calculus class, you have 2 topics that are of importance, and these are differentiation and integration. And so we can define on timescales the delta derivative in a very similar manner as you could do it in the continuous case using an epsilon delta approach. So we say that a function has a delta derivative denoted with f to the delta. Yeah, it's not a power, it's just a super index. If for all epsilon greater than 0, there exists a delta greater than 0 such that this inequality holds. And one thing to note is that if you are in the reals, then in this case, you would see that the sigma t is just t. And so you would obtain again the very traditional epsilon delta definition of a derivative that you may know from calculus. Again, that sigma t that shows up here is also important, as it then results in the case that if the graininess is positive, you obtain the derivative to be of this form f evaluated at the right next neighbor minus f of t divided by, again, this is the difference of the time, so sigma t minus t. And that may look very familiar. It looks a little bit like a difference quotient, right? Because you evaluate the function at the next time step. So you take the difference of the function values divided by the difference of the time values. And so just to note, if you were to choose t equals z, then your graininess would be 1. So it's certainly greater than 0. And your delta derivative collapses to f. Sigma t is the next time point, which is t plus 1 minus f of t divided by the graininess, which is just 1. And so this is your typical forward, the delta operator in difference equations. All right. Now, a relation that is rather specific to timescales and that is commonly used in research to simplify expressions and manipulate them is that f to the superindex sigma, which just represents f composed with sigma, so f evaluated at the at sigma t, can be expressed for a delta differentiable function as f plus mu f delta. Now, this sigma relation is not relevant in the continuous case, again, simply because f of sigma is f, because sigma t is t, you can get arbitrarily close. And we see that here in that case, mu of t is 0, and we do obtain f sigma t is ft. Now, as in the continuous case, the delta operator, our differential operator on timescales, is linear. And usually when one learns in calculus to take derivatives, you don't have to use an epsilon delta definition necessarily, simply because there were some rules that already used that epsilon delta idea and gave a very nice formula. And so the question would be, does there exist something like that on timescales? And certainly there is such a product rule. If you were to take the delta derivative of f times g, then you would obtain f delta. So that would be your derivative of f times g plus the derivative of g, but now it's not quite f, it's f sigma t. And so it doesn't matter where the sigma goes, you could also put it at the g, but it has to appear at one of the two functions, all right? And again, if you were to pick t to be equals to r, remember g of sigma is just g, and your delta derivative collapses to the usual derivative. And so you would obtain g prime f plus g times f prime. So that's the typical product rule that we know. However, if the time scale is not the real numbers, in particular, if mu of t is not 0, then there is such a dependency on sigma. And so if you were hoping for a power rule on timescales, then I have to somewhat disappoint you. If you were to take the delta derivative of t squared, then just simply because of that appearance of that sigma, we do obtain the derivative of, or the delta derivative of t, which is 1, but then we do obtain t plus sigma t, and that does not have to be equal to 2t unless mu of t is 0. All right, and then similarly for the quotient rule, you can obtain a formula that looks relatively similar as the continuous case. You do have f prime, so f delta times g minus f times g delta in the numerator. However, the denominator is slightly different. Again, we do get this dependency on sigma. And you can check very easily that in the continuous case, g sigma is g, and you obtain or recover the same quotient rule that you remember. Now, that sigma dependency is then, of course, impacting the delta derivative of a simple function 1 over t. Given the sigma here from g, we have minus 1 over t sigma t. And again, that does not have to be equal to negative 1 over t squared. So these are just some things to be aware of. There does appear that sigma every once in a while. Now, the second topic is antiderivatives or integration in the traditional calculus class. And so very similarly, now that we did define derivatives, we can use that to define so-called antiderivatives. And an antiderivative is a capital function f such that its delta derivative is equal to f for all t. And we define that integral here that you see, we define this so-called delta integral, that expression on the left, again, very similar to the traditional case as the antiderivative evaluated at the endpoints. And so just here an example, just given its construction that is so close to the real case, we see that for an interval, or if you pick t to be the real numbers, you would end up with the classical integration. If you were to, however, choose a timescale that consists of isolated points, then in this case, you would obtain the summation of the function values evaluated at these points. But note that the graininess is a new term that has to be considered. Yeah, so we also keep track of the distance between the points. And of course, if you were to have a combination, then you would want to choose, you would want to split that integral so that you can consider a continuous integral and then your summation. Okay, we are heading towards dynamic equations, and dynamic equations are, now that we defined the delta derivative, this is very similar to differential equations in the sense that a dynamic equation is an equation that contains a delta derivative of an unknown function. And so an exponential function can be defined as the unique solution to a first order, very simple dynamic equation, y delta equals pty, with the initial condition of yt naught equals 1. And of course, you would have to know or prove by that time that this type of dynamic equation only possesses a unique solution. But this unique solution is then called the exponential function. And so if we have a look just to verify if this definition of an exponential function makes sense, you would want to choose the timescale to be the real numbers just to see if there is a relation and if it does collapse again to the well-known results. And in this case, if you were to choose t equals r, your delta derivative is the traditional derivative, and you would obtain y prime equals pty. That's a first order linear differential equation that is homogeneous. And we know that the unique solution is given by that exponential function. So we do retrieve the traditional exponential function. However, in the discrete case, your delta derivative now is nothing else, and we did have that a couple of slides ago. It turned out to be yt plus 1 minus yt. And so if this should be equal to py on the right-hand side, you can, of course, rewrite that as yt plus 1 equals to pt plus 1 yt. And that's a recursion. And simply keep applying that recursion, you would end up then with the product of 1 plus the p's. So you end up with the product of 1 plus ps. Now, there are a couple of things that I would like to mention here. So the first one is a property that we know from exponential functions is that they are non-negative, right? In fact, is there a question? Okay. If there is a question, then please let me know. All right. So again, one thing that I would highlight here is that exponential functions are non-negative, certainly. This is, however, not necessarily true in timescales, as the timescales exponential function could, for example, oscillate. As we see here, it's a product. So if p of s would contain negative values, then you could get that oscillation between positive and negative values. I also would like to point out one importance here about this regressiveness that we saw earlier. It actually is nothing else. Here inside that product, we have the terms 1 plus 1 times ps, right? Which is nothing else than 1 plus mu t or mu s, sorry, ps. And if you remember, we actually said that we would regressiveness means that 1 plus mu p would not be 0. And this is certainly what you want. Otherwise, your solution, your product here would be 0, and you would just get the trivial solution. So this is why you would want to require, that the function is RD continuous and also regressive. All right, so if we define the exponential function on timescales as the unique solution to this first order dynamic equation, right? Simply because it turns out to be the same in the real case, you may ask, well, is that the only way to obtain a timescales analog of the simple differential equation y prime equals pty? And that's a valid comment because, of course, that's not necessarily true. There are other variations. In particular, if you were to put a sigma here on y, then again, if you were to choose t to be equal to r, you would also obtain y prime equals pty, and it would also be the same differential equation. So, well, which one is the right one? Well, it turns out if you were to have y delta equals py sigma, you would again obtain the same exponential function as in the previous case, but you would obtain this circle minus p. Now, what I would like to point out here is that in the real case, again, remember, in the real case, right, the circle minus turned out to be just the classical minus symbol, and minus would be positive. So even though there are two different, slightly different versions on timescales, they would collapse to the same equation in the real numbers, and also your timescale solution will be basically the same structure, right? It will be, again, if you pick t to be the integers, you would again obtain a product of 1 plus, and in this case then circle minus p. All right. Now, this is the solution to a homogeneous first order linear dynamic equation. And once you have the solution to the homogeneous case, you can also obtain the solution to the non-homogeneous case. So if you have a function f here, and in order for that integral to be well defined, we would want that function to be at least RD continuous. And so again, there are two different versions in a way that are solved in the same manner. And I highlighted here the differences in the solution in red. And so they look very similar. but there is a slight difference because you use circle minus minus p. But again, the structure of that E of that timescale exponential function remains the same. Okay, now the solution to those linear dynamic equations that are non-homogeneous plays a crucial role now once we get to solutions to non-linear dynamic equations, which brings me to the second part of the talk on applications. I'm just trying to see, okay, just so that I remain within the time, sorry. So in particular, I would like to focus on the application of population models. And if you, so the population models. And so one of the most famous population models that you may have heard of is the so-called logistic growth model by Pierre-François Verhulst, who recognized that a population possibly increases exponentially in the beginning. So we see that here, but then due to the limit in resources, it actually slows down and it approaches a positive carrying capacity. And so naturally, you may ask, well, what would be the timescales analog? Because this equation, although it's been around for so long, it's still being applied. And yes, it's being modified by including delay, for example, or extending it to PDEs, including a spatial component. But it forms the foundation for a lot of the models that are still being investigated. And so one would be interested in trying to unify that model as well and finding a corresponding analog on timescales. And so this is a result by Bono and Peterson. That was the second book that we saw in the very beginning, Advances on Timescales, that provides the explicit solution of that non-linear node. It's non-linear because you have a y sigma and a y here, but it still provides the explicit solution of this non-linear dynamic equation. And it also extends it in a way slightly to the classical Verhulst model because it does allow for time-dependent growth and time-dependent carrying capacity. Now there is an analysis of this model that you can find, and I did provide here the reference by Carlyle, Gore, and Weber from 2011, if you're interested in the global dynamics. Now, the reason, so one possible criticism or one possible question would be, how does one know that this is to be considered the unification of the logistic growth model? Yes, it's a nonlinear dynamic equation, but how does one justify that this is indeed should be considered as a unification of such a model? Well, first off, if you were to choose t to be equal to r, your delta derivative collapses to the classical one, and your y sigma is also reducing to the classical just a y value, and you retrieve the classical logistic model. But not only that, also if one takes a look at the solution method, it's actually the same method how one can solve the logistic growth model. Using a substitution of 1 over y, of course, first showing that for positive initial conditions, the solutions remain positive, then this substitution is valid and well-defined. You then obtain a first order dynamic equation that is linear and non-homogeneous, which we just saw can be solved using the variation of constants method. And of course, this is the same in the continuous case. And at every single step, once you end up with your solution, right, you obtain in the same way your solution in the real case. And clearly, if you were to just take a look at the solution and pick t to be equals to r, you again obtain the classical solution to the logistic growth model. So there are these parallels. And so this could be or should be a justification as to why this should be considered a unification of the logistic growth model. Now, once we accept that to be a unification, then of course you can also choose other timescales. And again, one of the most common examples would be then the integers. And if you were to choose the integers, you obtain a so-called difference equation. And that difference equation, which again, remember, difference equations are being studied by separately somewhat. This is a difference equation that for difference equation modelers is somewhat strange. And the reason for this is that there is a yt plus 1 on the right-hand side. So a lot of the criticism would be, well, how does the change of the population depend on the next time step? And it does seem somewhat strange. However, you can rewrite a difference equation as a recurrence. And once you write it as a recurrence, it actually is the same as the well-known Beverton-Holt equation. And the Beverton-Holt equation was investigated and is accepted by difference equation modelers and was well studied in the 50s by Raymond Beverton and Sidney Holt in the context of fisheries. Now, I should mention that there are other discretizations of the logistic growth model. We see here a famous one that is the so-called Ricker model, or another one is the logistic map that was introduced also by Robert May and then led ultimately to the study of chaos. Now, although those recurrences that we see here are in blue are valid recurrences, and they exhibit interesting behavior due to their chaos that they can exhibit for large R values. The question is whether or not they should be called a discretization of the logistic differential equation. And if you have the opinion that a model should be called a discretization because it exhibits similar behavior, or in this case is under the umbrella of the unified timescales model, then of course you would conclude differently. Now, as I mentioned, this is the well-known Beverton-Holt equation or recurrence that was introduced in that book from 1957 on the dynamics of exploited fish populations. Now, for that Beverton-Holt model, beside the point that you can solve it explicitly, and that shouldn't be a surprise because we know the explicit solution to the logistic dynamic equation. Well, so if you choose the timescale to be the integers, you obtain the solution to the Beverton-Holt equation. So that shouldn't be a surprise. What's interesting, though, is that there has been a study by Jim Cushing and Cushing-Henson, or at least initiated by those two, where they recognized from an experiment with flower beetles that if you were to introduce a periodic environment to a population that is being modeled via the Beverton-Holt model, that this introduction of the periodic environment is in fact deleterious for the population. So what that means is that if your environment is omega periodic, then you have a unique omega periodic solution, Y bar. So the population converges to that unique omega periodic solution. But on average, that solution is strictly less than the average of the carrying capacities. And there's only equality if the environment would not be periodic, if it were constant. So that means that the introduction of a periodic environment would actually reduce the population, at least on average. And so, well, given that there is a relation between the Beverton-Holt model that we see here on the right and the real case under the umbrella of our general timescales model, a natural question would be whether or not these conjectures uphold for the overarching timescales model. Or spoken differently, that means, do these conjectures uphold, does a periodic environment immediately result in the reduction of the population on average, or is that just an artifact of that very specific time scale? So the question that we want to address is whether these Cushing-Henson conjectures uphold for that overarching timescales model. And as a first check, Well, we could just check these conjectures for the real case, right? We certainly know that this is the logistic differential equation, and it's not hard to show. In fact, you can follow the same idea, and you can show that it turns out that if the carrying capacity, so your environment, is omega periodic, so that should just be the carrying capacity, R is 1 periodic, then there exists a unique omega periodic solution that is globally asymptotically stable. And that omega periodic solution is on average, in this case, we have a continuous average, of course, is strictly less than the average of the carrying capacities. So the Cushing-Henson conjectures uphold in the real case. So now that this was the first check, let's see if we can address that on timescales. Now, the problem is that if you want to consider the impact of a periodic environment on timescales, you would have to define periodicity first, right? And the simple problem is, take, for example, a time domain where you have the point 1 and let's say 3, 4, and then maybe 10. Well, you wouldn't be able to find something that is 1 periodic simply because functions wouldn't be defined at t+1 necessarily, right? We are not defined here at 2. So how would a function be 1 periodic if not all the points are in there, right? And so to avoid that type of problem, a very common assumption is that you keep the definition of periodicity, but you choose your time scale to be omega periodic, right? So then you avoid that whole issue. You assume that t plus and minus omega are both in your time scale for all t. And this type of assumption is very common. And you see here 2 examples, but of course there are many more. 2 examples where these assumptions are being used specifically for population models and discussing the existence of periodic solutions. Now, I should mention that there are some other authors that would call such a timescale to be an almost periodic timescale, but it's more commonly known as an omega periodic timescale. And for such a periodic timescale, Bohner and Ward proved in 2007 the Cushing-Henson conjectures. So the Cushing-Henson conjectures, again, if your environment is omega periodic, then you obtain a unique omega periodic solution. And on average, that periodic solution, the average of the periodic solution, is strictly less than the average of the carrying capacities, where equality holds if K is constant. So the answer would now be yes, the Cushing-Henson conjectures uphold if you consider a periodic timescale. Well, but this is a very restrictive subset of timescales that are possible. Remember, a timescale is an arbitrary non-empty closed subset. Forcing it to be periodic is very restrictive. And you see here again, one of the common examples, q to the n, in this case, choosing q to be 2, is already not omega periodic because t plus or minus omega for any omega would not be in your timescale for all t. There are many more examples. So in order to address specifically the first case, simply because it's one of the most common examples and because it has applications in physics, one would have to look at how can one define periodicity of a function, even though the time domain is not periodic. And so how would one be able to capture that the value repeats, for example, in this case, after 3 time steps? Well, this is something that Bohner and Chio-John in 2012 introduced, at least for the quantum calculus case. And they said that a function is supposed to or should be considered omega periodic if, and now this is q to the omega times the function evaluated at the omega step after t, and that should be equal to f of t. And in that paper, the definition was provided because it then resulted in the proof of those Cushing-Henson conjectures. And again, if your environment is considered to be periodic, and here we really talk about this new periodicity where we require periodicity, so Q omega f of Q omega t equals to f of t. And at that time, it wasn't really motivated, but it was certainly something that made the problem rather nice and solvable. And at least the first Cushing-Henson conjecture was again satisfied. There exists a unique omega periodic solution that is globally attracting. However, the second Cushing-Henson conjecture did not uphold, as the average of the unique omega periodic solution was less than, and now it's not the average of the carrying capacity, but this additional term that would be multiplied, like a multiplication factor where I should say that alpha was equal to A over T. So this capital A that you see here was related to that growth rate, right? All right. So in a previous slide, we called it R. So I apologize, I should have been consistently using R. Okay, so we have this multiplication factor dependent on the growth, and but it doesn't uphold in the classical case. All right, so since we now have the Cushing-Henson conjectures, at least for the By-Wattenholt model, we have it for the real case and it works fine. We have it for periodic timescales and they both uphold. We see already that in the quantum setting, in the quantum calculus timescale, it does not quite uphold. Only the first Cushing-Henson conjectures regarding the unique omega periodic solution holds. But there is still a large set of timescales that are not being addressed. And I should point out before I get to the actual periodicity idea that I would like to cover today, I should mention that there is from 2013 by Murad Adiva a way to define periodicity for a broader class of timescales. Now, I don't want to go into details here, but what I would like to point out is that Murad Adiva is defining first a timescale that is not quite periodic, it's periodic in shifts. So that already relaxes the condition of a periodic timescale that was so restrictive. It relaxes it now to finding those shift operators, that those two functions, such that your timescale would then consider to be omega or periodic with respect to those shifts. Now, the problem here is that you have those 5 conditions that your shift functions would have to satisfy, and those shift functions you have to find first. Now, once you have them, you can then define, and again, I don't want to go into details here, you can define periodicity of functions for such a periodic timescale that is periodic in those shifts. But the difficulty is to find those 2 shift functions that satisfy all these 5 conditions. And although the author, Murad Adiva, is providing a table with classical timescales and their corresponding possible shift functions, it is, however, a problem to do or to find these shift functions in general, and they don't have to exist. So here are just 2 examples, and there are many more that you can construct where no such shift operators do exist. So again, what that tells us is it doesn't cover all timescales, and it certainly can be rather extensive to try to find such shift operators. So in 2019, Martin Bona, in a workshop in Poland, posed that problem of periodicity on timescales. And so we got together and we, Jacqueline Mesquita and Martin Bona and I, we got together and we tried to think about it in a different way, trying to define periodicity in a rather elementary way. And what we were able to do is to to define periodicity for isolated timescales. So again, it doesn't cover all possible timescales. It's again just a subset of timescales, but it's a rather broad set of timescales, and we will obtain a very easy way of checking that. And so just for you, it's still an open problem. And okay, now for isolated timescales, isolated is, if you remember at the very beginning of this talk, an isolated point was a point that you couldn't get arbitrarily close from either side. And so we consider an isolated timescale to be a timescale where every point is right scattered and left scattered. And so what we would want to do is kind of think about the very simple example of an isolated timescale, namely the integers. And so we see here an example, we would consider that to be 1, 2, 3, 4, 5, 6 periodic, because the function value repeats after 6 time steps. And so again, we would classically come up with f of t being f of t plus 6 in this case. However, it's not only the function value, you can also think about this slightly differently using areas of rectangles. So if you were to consider the function values here, that's your blue points. I hope that you can see that. So we would have a 3 periodic function in the, following the traditional idea of f of t plus 3 being equal to f of t. And the function value would be the height of your rectangle, and the length of the rectangle would be the distance between the points. Now, in the discrete case, the distance between the points, so your length, would always be 1, just because of that time scale, right, the integers. And so in this case, really the area of the rectangle would be solely determined by the height, which would be your function value. This idea of areas, however, provides an opportunity to extend that to isolated timescales that are not where the time points are not necessarily 1 apart. And so if we would say that we define periodic if the areas repeat, then this example, of course, you can continue this, would then be considered 2 periodic if again those areas keep repeating. And so the purple area is the same after the second area basically. And how do you obtain the area of such a rectangle? Again, it would be the height, which is determined by your function value, but also the length of the rectangle. And that length of the rectangle is the difference between those 2 points. And remember so the right next neighbor that we denoted with sigma x1. And so their difference was nothing else than mu, our graininess at x1. And so similarly, of course, then the area of the green, the height is determined by f of x2. And then the length would be the distance between the right next neighbor of x2 and minus x2, which would be the graininess x2. And so we see, as I just mentioned, that the ETH area is the function value times the graininess, so times the length of the area. And so that ultimately resulted in the theorem, and I would like to point out this first, because it's just because we ended with that. So the area of the rectangle at T is equal to the area of the rectangle omega steps later. So this sigma omega t is basically omega steps later, very roughly speaking, okay? And you can equivalently, since mu of t is not 0 for all t, you could divide both sides by mu of t, and that would then give you a slightly more compact version of that. That also looks possibly more sophisticated, where you have f of t equals to this nu delta, and nu delta is nothing else than, so nu delta, yeah, this is really nothing else than mu of sigma omega t divided by mu of t. Yeah, all right. Okay, so now accepting this rather simple condition, really it boils down to basically proving or checking if the function f satisfies this equation rather than looking for shift functions. And so I know that we are heading towards the end, so I will try to close it up. We see here an example. If you were to choose the integers, I denoted it here with TI for isolated timescale, just so we remember it's really a definition for isolated timescales at this point. And if you were to choose the integers, then the graininess is equal to 1. And the omega step after t would be t plus omega, right? So then our condition, which is mu times f equal mu sigma omega t, f sigma omega t, area t equal area of omega time steps later, would then just be f of t plus omega, because that guy here is 1. And similarly, since this is 1, we obtained a very traditional a case of periodicity that f of t is equal to f of t plus omega. And so another very special case here would be the quantum calculus case q to the n0. Sorry, in this case, the graininess we saw very early on in a table, right? Or you just calculate it again, q of t minus t, so q minus 1t. And omega time steps later, again, remember it's a multiplicative time domain, so that would be q omega t. So then the condition of the area at t equals the area omega time steps later would be q minus 1t times f at t, and the area omega time steps later would then be given in this form. And so what we see is after canceling q minus 1 and t, of course, we don't want t to be 0, but t is in your time scale, and q to the n0 will never be 0 for q greater than 1. And we obtain the exact definition of periodicity that was provided by Bona and Giojan in 2013 when they discussed the Cushing-Henson conjectures. But in this way, it's actually motivated for an even broader class of timescales, the isolated timescales. And there are some nice properties. The periodicity carries over through several operations such as circle plus, circle minus, multiplication of a constant, the typical addition and subtraction. And of course, we kind of picked the definition of periodicity so that the integral over omega time steps remains the same, right? Remember, it is nothing else than the areas. And of course, then it doesn't really matter where you start counting these areas in a way. And what's also interesting is it turns out that a function would be considered one periodic if and only if it's of the form a constant over the graininess. And there are some really interesting things. Just something to note is in the continuous case, a constant function is automatically, or in the discrete case, a constant function is always one periodic. So the question of choosing constant coefficients or one periodic coefficients now becomes a whole different meaning. Yeah, and so just to finalize, using that definition of periodicity also allowed us to now address the Cushing-Henson conjectures for our logistic dynamic equation that can be written in this way. So like a generalization of the Beverton-Holt. And you again, it looks possibly a little more horrific, but it certainly tells us that there is a unique omega periodic solution and that this omega periodic solution is globally attracting. And the second Cushing-Henson conjecture is again not quite true. We didn't expect that because we didn't expect it to hold because we know from quantum calculus that it doesn't quite hold. But we do get a precise description here. The average of the unique omega periodic solution is strictly less than, now we have these additional terms. And just to point out that if you are in the discrete case, your sigma delta is just 1. And so you would have that term to be 1 over 1 minus c. Those cancel out and you get exactly the average of k. I know that this is, a lot, and I didn't go into detail of what this theorem all tells us, but the point was really just to say that this new definition of periodicity allowed us to now address these Cushing-Henson conjectures for an arbitrary isolated timescale. So I will leave it with that, and thank you for your attention and take any questions. So thank you. Are there any questions or?
Any question from our participant?
Hello.
Hi.
Hello. Good morning. I think
Yeah,
it's good evening to you.
Yeah, nice. Yeah.
Okay, it was a quite interesting presentation, and the idea means the concept was totally new for us, but it's very interesting. And what I want to ask you that why particularly this kind of closed sets are called time scale?
Also, this is just because Stefan Heger called it a time scale. So there is no specific reason. He just defined a time scale to be a non-empty closed subset of the real numbers. I mean, it's really his, I mean, in a way, it's his definition, right? There was no such thing as a time scale before, at least. I mean, there are researchers who use the terminology of timescale, but they use it rather differently. So if you go online and you look for some papers on population dynamics, then I did already find like 1 or 2 papers where they talked about timescales in a very different manner. And sometimes it is considered to be in a statistical setting or in a biological setting, but it's very different to the mathematical definition that Stefan Hilger gives, and he just defined the timescale to be that. I mean, yeah, the closeness does make it, of course, rather nice because you don't have to worry about limit points not being within the timescale, and so you can nicely define, of course, differentiation and integration without having to worry about something like that. Mm-hmm.
Okay. Another question I want to ask, you wrote their population model, yeah, and its equivalent model when you are writing that as y delta.
Yeah. Mm-hmm.
So means how you define that y delta equivalent form, whether you get it from differentiation that form, or means what was the idea?
Yeah, very good question. And the answer is it's a little bit trial and error, to be honest. And so the reason for this is, let me share the screen one more time. It's a really, really nice question. Okay, so let me share. You should be able to see the screen now. Let me go back. So the traditional case of a logistic differential equation is this form, right? And so if you were interested in finding logistic dynamic equation, I mean, theoretically, you can use whatever you can claim that any nonlinear dynamic equation would be an analog, but of course that would be very controversial because you would have to somewhat justify that this is supposed to be considered a unification. In order to find it, well, one thing would be certainly you wanted to collapse to the traditional case, to this logistic differential equation, once you choose the timescale to be R. So as a first step, usually one considers to change the derivative to y delta. Again, this is, just the first step. However, now you see those y's floating around. And the problem with that is, that on timescales, a y sigma is not equal to y. However, if you choose t to be equal to r, it collapses to y. So you could, one thing is to choose y sigma here, which is exactly what has been done. But alternatively, you may also want to consider the delta sigma here inside the parentheses, right? Because again, if you were to choose the timescale to be the real numbers, it again collapses to this differential equation. So now you have these two forms, and the question is, are both of them valid? very similar to how it was in the variation of constants way. There were two different forms. Both of them were valid, and both of them were justifiably a unification. Now, the issue with this one, as you go through and analyzing it, is first, you may not find a unique solution in exactly the same way. And second, although I think you certainly will. And then the second one is to check the behavior. Since you claim that it is a unification of such a model, you would want to have properties to be similar. Now, of course, the underlying time domain may change the behavior of solutions, but optimally, it should at least preserve some of it. If you end up with a chaotic solution or chaotic system, that should make you question whether or not this really should be considered a unification of the logistic differential equation. And of course, you can think of many other versions where you put sigmas on both sides, or you don't put a sigma anywhere, right? Yeah, so it's a little trial and error. I'm pretty sure that this one doesn't give you any unique solution, nor does it give you the similar behavior. And then similarly for the case where you don't put a sigma anywhere, if you were to put a sigma in the parentheses, then possibly it may still work. Yeah.
Okay.
Thanks. Good question. Yeah.
Okay.
Thanks.
Okay. One last question.
Yeah.
Because y delta, when we write t is r, so y delta is transformed into y dash first derivative. So
yeah.
Can we say that y delta are the generalization of derivatives? Can we say that?
Yeah, exactly. That's it. So this is called a delta derivative, and that would be the unification of a derivative in the classical case. Yeah.
So if just like we have a geometrical meaning of y dash first derivative, so whether there is any geometrical meaning of y delta?
Yeah, so that would be exactly the same. You would also talk about the change. It captures the change of your function value divided by the change of your time domain. Yeah, it would be a very similar interpretation as in the continuous case. Now note in the continuous case, really there are different ways to define derivatives. So f prime or f dash. One way is to use that epsilon delta. Another one that you may have learned is the limit definition, right? So really what you take is the limit as of a difference quotient, correct? And so that difference quotient is the change of the function value divided by the change of the time values. And so this is exactly the same, and it does collapse that f delta, the delta derivative, is actually, if you can get arbitrarily close, you would basically take that limit of that difference quotient, the difference in f, and divide it by the difference in t. Otherwise, you would then just obtain that difference in f divided by the difference of t. So yeah, the interpretation would be the same. And the only thing to watch out for is, again, this product rule and quotient rule. There are slight differences. And one thing that I didn't mention is actually the chain rule. There are different versions of the chain rule. They turn out to be equivalent, but they are not as nice. And therefore, and what I mean with nice is they are not as powerful. So in differential equations, some of the tricks how to solve specifically nonlinear differential equations is to use a chain rule method to rearrange variables or define new variables. That's much more difficult in timescales because you don't really have that chain rule in the same way. It only upholds in a modification that is not as powerful. So that's a little bit of an issue. Yeah. Okay, so there are many open problems still. Yeah, thanks for your question.
Okay. Thank you so much for the interesting talk. Thank you.
Thanks. Thank you. Thanks for asking.
Hello, Miss. Hello, ma'am.
Hello.
Yeah.
Hello, ma'am. Myself, Hemanto College, research scholar of Guwahati University. Well, from the beginning, I was not able to in the talk actually. But you told, ma'am, can I know about the fractional dynamic equation? How can we use a jump operator in fractional dynamic equation for non-absolute integrable function like Hanstrock casual integration?
I'm very sorry. So I gave that. It's a good question. but at this point, I cannot give the answer. I'm actually not working in that area. I would, however, recommend, so I know that Alan Peterson, he has a book on fractional calculus, right? But Svetlin Georgiev in 2018 published a book on fractional dynamic calculus. So I'm not familiar with that topic, so I would recommend to take a look at that. I'm sorry, I cannot answer
No, it's
that
okay.
question.
It's okay. Thank you, ma'am. It's okay. Thank you very much, ma'am.
Thanks for asking.
Any more query from our participant?
Hello.
Yeah,
Hello.
Yes,
Madam,
yes.
I have one question.
Yeah.
Madam, thanking you for very nice presentation. I have a question about the application of fractional time scale analysis. Is it extended up to the nonlinear partial differential equation like KdV, ZK equation?
Sorry, nonlinear partial differential equations? Was that the question or did I misheard?
Yeah, nonlinear evolution.
But partial differential
Is it
equations.
extended partial, especially nonlinear partial differential equation, like KdV equation, ZK equation, evolution equation?
I'm sorry. I'm sorry. It goes in and out. Is it? Did you ask? So I understood non-linear, but is it? Are you asking about partial or stochastic?
Nonlinear
What
partial differential equation.
Oh,
Is
sorry.
it extended?
Okay. No, I did not see a paper on nonlinear partial dynamic equations. So they would consider to be partial dynamic equations, right? And there's actually not too much work there. So the introductory paper I would recommend is, for example, from Jackson, partial dynamic equations on timescales. And there it's really just the idea that is being introduced. And there are papers on partial dynamic equations, but there are just a few of them. So it's still a very open area. And that in particular, if you want to look at very specific nonlinear dynamic or partial dynamic equations, you have something in mind that you would want to try to generalize to timescales, then yeah, I would recommend to take a look at a paper by Jackson and then use that framework to extend it. I also would say that there's, again, quite a potential to be, to discover some new results. So if you work on partial differential equations, then it would be worthwhile to take a look at partial dynamic equations, at the corresponding equations there. And yeah, just to keep in mind that, again, those y's and y sigmas do matter. Yeah, I hope that answers the question.
Okay, thank you.
Yeah.
Thank you.
Thanks for asking.
Okay.
Any more query, please? Any more query from our participant?
Yeah.
Okay.
Yeah, Hemant, I have just one quick question. So, hello.
Okay.
Hi.
Yes.
Hi. Yeah. So I am Syed Abbas, and I work on time scale. Sorry. So it's just a quick question. What is the main difficulty with partial dynamic equations?
Yeah, I think so. The difficulty is already when you take a look at partial difference equations, right? The issue is a little bit as you make your grid to walk along, that you have many different possibilities. And the question is really just to define even the space that you would want to consider, beside the point of then talking about taking derivatives on either one of those variables. So I think that this is one of the reasons why, I mean, with this paper, it was introduced, but then after that, there's not too much work that is being done. So I think on Math Scinet, you find about possibly 11 papers or something. So yeah, I mean, if I would want to do partial dynamic equations, I would possibly first take a look at partial difference equations. And once familiar with that idea, just to even set up the space that you would want to look at and then the derivatives, then I would go on to partial dynamic equations. It's also a little bit of an issue because this is a paper, it's not a book, right? So for example, if you take a look at timescales, there have been quite a few books. Even the fractional timescales is a book, but you won't find that on partial dynamic equations. For stochastic dynamic equations, one of the issues is that, so with stochastic dynamic equations, it's a little bit similar. So there are only just a few papers. It was introduced a little later, but there are also only few papers. And there you have the problem, although you don't get this two-dimensional or even higher dimensional grid with a variable that you would have to consider, you do have the problem that a lot of the stochastic differential equations use the normal distribution, right? And even though there are normal distributions defined on timescales, they are not exhibiting the same, again, nice properties. And in this case, what I mean with nice is something like that the expected value would always be mu, and that the variance is a sigma squared, you know. So there are some properties of a normal distribution that one uses when discussing stochastic differential equations, but those properties are not necessarily satisfied by the normal distributions that are defined currently. So there are still many open problems that one could work on.
I think there is one thesis by Suman Sanyal on stochastic dynamic equation.
Yeah, exactly. Yeah, there are different. There's also one by Thomas Matthews, a student by Martin Bonas. And he also, in his PhD thesis, he also discusses stochasticity on timescales. And he also provides a normal distribution. So I'm not claiming that there are no normal distributions. They are, and again, some of them are, of course, very useful, but it just depends on what exactly you want to do with them. Yeah.
Okay, thank you. Thank you so much. It was a really nice talk.
Thank you very much. Thank you.
I guess there is no more question from our participant. So thank you.
Yeah. Hello.
Yeah, do you have any question?
Yeah, Rajendra here from Mumbai. May I get in for a while, for a few minutes?
Yeah.
Is it on? All right. Hello, Professor. Good evening. I suppose this is good evening there, right? Am I right? Yeah.
Yes. Good night. Yeah.
This is good night. I'm so sorry. This is Rajendra from Mumbai. Mumbai. I am actually in one of the colleges. I'm a teacher of a college actually in Mumbai.
Nice.
I just due to some network glitches in between, it was a little difficult for me to hear you and the entire this one. I was keep on struggling about it, but then due to certain glitches,
I'm sorry.
talks. No, it's not from your side. It is from my side actually. So due to that, I couldn't. So my point was like. Basically, my area is number theory and topology and all these kind of things. But then this area is a little new for me, actually. I just wanted to know from you, like this one. 1 second. Wait, just a minute, please. Time scale calculus is basically dealing with like discrete branch. Am I right? Yes. So
sorry to interrupt. Not quite though. So it really tries to unify the continuous and the discrete time domains. So specifically, So specifically, once you get to differential equations, right? We know that if you take a look at difference equations, they can behave quite differently, right? For some of the simple difference equations, you get chaotic behavior, while you don't obtain that in the continuous case. So this is just one example. And, you know, this tries to motivate also to unify those branches and to see, okay, what would be the corresponding, what would even be a derivative in a unification way, in a sense, instead of giving a calculus class in the continuous case and a calculus class in the discrete case, you could theoretically just put it all together and give a timescales class, right? And then, of course, you could study those dynamic equations which are essentially analogs of differential equations, but on this general time domain. Mm-hmm.
Yeah, thank you. Yes, I was like under that impression only, like because I was, in between, I was able to attain because of the network glitches, as I told you. In between, the examples were all about Z and all those kind of things. So I thought it is purely discrete kind of, and not like, continuous. I was like thinking like it is all about difference equations, rather this one, what to call, the actual form of calculus, like, continuous form. Yeah. So I was under. Yeah. So thank you very much. And one more
no
thing
problem.
is like, yeah.
So
one
these
more
are
thing
just
is like,
some examples that are.
yeah.
So
Yeah.
you see the last one, it's not necessarily discrete. It does contain patches where it's continuous as well.
Correct. Exactly. And then all about the closed set, because time scales are, we are taking closed sets on R, I mean real line, possibly because like it is, I'm just asking, I'm not sure about what I'm actually saying, whether I'm asking a vague question, but is it because of the closed set is containing all its limit points or something like that? Densities,
Yeah,
because
exactly.
you're talking. Yeah. Thank you.
You do want to. So this is also an example where you can define the space to be a sequence, but then you really want to make sure that you contain its limit points so you don't run into any problems later on. Yeah.
Exactly. Thank you very much. Thank you. Talks were excellent. Yeah. Thank you.
Thank you very much. Thanks.
So I guess there is no more question from participant. So thank you, Dr. Sabrina Steipai, for accepting our invitation and delivering a very interesting and useful talk.
Thank you very much for inviting me.
Yeah, now I request Dr. Dipankar Sharma from Jawaharlal Nehru College to offer vote of thanks. It's over to you, Dr. Dipankar Sharma.
Thank you, Hemant. Am I audible?
Yes, you are audible.
We are at the ending moment of our today's lecture session. It's a very fruitful lecture from our resource person. At the program, the moment of vote of thanks. At first, I would like to offer our vote of thanks from our organizing team to our inaugurator, Principal Sir, Dr. Tapon Datta, for his delivering lecture to inspire us